So chemistry is basically the study of matter, right? And everything that has matter has mass associated with it. Okay, and so we kind of broke up matter into kind of three major components. We have what we call the macroscopic, the microscopic, and the particulate. Macroscopic is what we can see with our eyes. That's kind of like me, or a sheet of paper, or a ring. Microscopic is what we can see with the microscope. So that's kind of like a plant cell, animal cell, bacteria cell. And a particulate are those that you can't see with either your eyes or your microscope. You have to use, or a traditional microscope, a light microscope. You have to use a special instrument, such as an electron microscope or something along those lines, or you're not able to visualize it at all. Okay? And so they're so tiny that you can't see it. Okay? You guys get that? More or less? Okay. Other than what's on the screen right now, can you guys, let's see. Kristen, can you tell me something that is macroscopic?
Myself.
Yourself, okay?
Mm-hmm.
Let's see. Is it Jetsim? I'm gonna butcher. Jetsimini? How do you say your name again? Jetsimi? Is it Jetsimi? You've got to unmute yourself.
Hetsamani?
Jetsimani.
Mm-hmm.
Jetsimani, tell me something you can see with a microscope or microscopic.
A pencil?
Can you see a pencil with a microscope?
Yes.
Can't you see a pencil with your eyes? I have a pencil right here.
Oh, a snowflake?
A snowflake. Can't you see those with your eyes too?
Not.
Something that you have to use a microscope to look at.
Germs?
Germs. Okay. Yeah, germs. Bacteria. Eukaryotic cells. Yeah, germs. Okay, cool. Let's see. Jessica, something that is a particulate. Something that you can't see with your eyes or a microscope, but it's so tiny that you have to use a specialized piece of equipment, such as an electron microscope or a scanning tunneling microscope.
Water molecule.
A water molecule. Yeah, that's good. Good. Okay, so because we can't see things with our eyes, a lot of times we have to use a microscope, or we have to use that specialized piece of equipment. For us to sit there and work with it and understand it and learn about it, we have to use modeling. And so often we will use models for making atoms and for making molecules. The most common models that are used, one is called the ball and stick model. Why do you think it's called the ball and stick model? Roberto.
So it's like a 3D. It's like trying to
So why do you think we call it ball and stick?
It's like to represent like honestly, I don't know. Like the atoms that connect them, maybe.
So why don't we call it toothpick and straw?
It's easier, I guess, to name.
Isn't it because it's a ball and stick? So if you look at the model down there, what is it?
A ball and a stick.
It's a ball and a stick. Okay, so we call it a ball and stick model because we're using balls and sticks. Okay, so the balls represents the atom. So the white atom there, in most cases, white atom represents hydrogen, and the black atom represents carbon. So how many of you guys know about methane? Know anything about methane?
Yeah, it's a type of gas, right?
It is a type of gas. That's right. CH4, methane. Do you guys know where it's most commonly found? Do you like burgers?
Yeah, I was trying to find like A polite way to say it.
So let me say it non-politely.
Yeah.
So it comes from cow farts, okay, or cow dung. So a lot of methane basically comes from cows because they fart or they poop. And if you guys ever come by Kalinga, so I teach at West Hills, Kalinga, and I live closer to West Hills than I live to Salinas. So Kalinga is right next to Harris Ranch. Do you guys know what Harris Ranch is? Harris Ranch is, they're the in California, they're the leading distributor of beef in California. And so if you want a really good steak, go out to Harris Ranch. It's delicious. You're probably a vegetarian, aren't you? You're making that faces, Kristen.
No, I was just still thinking of methane.
Anyway, so methane is made up of carbon and hydrogen, two different atoms, right? And we'll talk about this here in a second, but that's considered to be a compound because it's two different atoms. But they're sharing what we call electrons. I'll talk to you about electrons here in a minute as well too. And that's the bond that they're sharing. And so that stick represents that bond of sharing those electrons. Okay, so often we'll have to use the ball and stick model to represent the three-dimensional representation of the molecule. Or we'll be using the space filling model. Often you'll see that on a computer screen or something like that. And you can see why it's called space filling as well. You just got these balls that are taking up space, right? So we are just talking about methane. So in addition to the concept of modeling, we often will use symbols to represent the chemicals that we're talking about. So we use letters. So, or one letter or two letters. Like for instance, hydrogen will use an H. Carbon will use a C. And so this makes it a little bit easier for us because we're scientists. And as scientists, we like to be brief, concise, and lazy, right? So we want to write things real quick and be able to convey information real quick without writing an essay, right? So we use chemical equations to let us know the chemical reactions that are going on. So we'll be using those symbols. And so you need to learn how to use those symbols. And I know that some of you guys already know this, but I'm going to take the assumption that we're just learning it all together until we get to, you know, the third chapter, and then we'll just go into second gear, okay? So you guys have heard of H2O before, right? What does H2O stand for?
There's two hydrogen molecules and then one oxygen.
Okay, so
That
what
would
is
be
the
water.
Water, yes, that was my next question. Common name that we use for two hydrogens and one oxygen together is water, right? Okay. Okay, speaking of water, are any of you guys kinesiologists or planning to be a kinesiologist major? No? Okay, well, that's too bad. You guys know what kinetics mean or kinesiology means?
It means like, it refers to, I was reading it in the book, it's like motion.
Movement, yeah. Yes, movement. Okay, so do you guys know the three states of matter?
Yes.
We're on a roll today. What are the
Solid,
three states
liquid,
of
and
Christian?
gas.
What was that, Kevin?
Solid, liquid, and gas.
Solid, liquid, and gas. Okay, so we're talking about water. So when we're talking about water, is water a solid, liquid, or gas?
A liquid.
Okay, what do we call it when it's a solid?
What do you mean?
What do we call water when it's a solid?
Oh, like ice.
Okay, and then what do we call it when it's a gas?
Vapor?
Vapor or steam, right?
Okay.
Yeah. Vapor or steam. Okay, so those are the three states for water, right? Or H2O. So in that case, H2O, is it changing its chemical formula when it's ice, liquid, when it's ice, water, or steam?
No.
No, it's not changing its state. So it's just changing its physical form, right? Because ice is a solid. It's just this block of thing that we have. We could put it on the table. As long as it's cold enough, it'll stay there and it'll stay in that block form, right? Stay rigid. Water, well, water we have to put in a container unless we want it to spill all over your table, right? Or steam is going to occupy the entire room, okay? So how do I get from ice, water, to steam? Carla.
How do we get from water to ice to steam?
Yep.
Well, water freezes to become ice, and then ice melts, like using heat to become water.
Oh, so are you telling me that temperature changes causes this to happen?
Yes.
Oh, okay. So temperature can cause things to happen. Have you guys ever been on a hot beach? You guys are in Salinas. Aren't there beaches there?
Yeah.
Yeah. So what happens on that day that is really, 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 really hot and you're out on the beach, you're barefoot on the sand? What do you do?
What do you mean? What do I do?
What do you do? If the sand is really, 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 really hot and you're
Then you go in the ocean.
So are you moving slow? Are you walking to the ocean, you know, looking cute? Oh, I'm just gonna
No.
diddle daddle to the ocean. Are you running to the ocean?
Running to the ocean, yes.
Yeah. So you're running to the ocean, right? Why?
Because the sand's too hot.
Because the sand is so hot, it causes you to move even faster, right? So just like that sand being hot, the molecules, the water molecules, are also going to be moving faster. So ice, have you guys ever been to a nightclub? No? Yeah, maybe. None of you guys turn up. Go to parties?
Yes.
Yes. Okay, one of you guys turn up. The rest of you guys are always at home, right? Okay, so if you're at a nightclub and that nightclub is so packed, or a dance or a party, and it is packed, and you want to dance, right? How do you dance? Are you doing this? You know,
No.
just a little move because there's nowhere to move. It's so congested, so packed. So you don't got a lot of room to move, right? So that's kind of like what's happening with ice. It's moving very little. So you get very, very little movement in the case of ice. Now water, on the other hand, right? That's kind of like when the dance floor is a little more spacious. So you're able to sit there and get your groove on, you know, hey, you know, get it going, right? And then if the dance floor is empty, you can take up the whole dance floor and you can do whatever you want to do. You can get all crazy, right? Okay, so that's exactly what's happening with these molecules. These molecules are going to be moving, right? Case of ice, very little movement. They're going to be packed together, close together, organized, right? So you have to do that little line dance, you know, so you can actually make use of the floor if you're going to move, right? Organized, right? And then if it's water, then you're able to sit there and do a little bit more. And then if it's gas, you're all over the place. Okay, and that's going to be dictated by temperature. The higher the temperature, the faster the molecules are going to move. Okay, so that is the kinetic molecular theory. Kinetic meaning movement, molecular means molecules, theory. Well, molecules are moving. So we talked about the three different states: solid, liquid, gas. So with the solid, there's two types of solids. We have what we call the crystalline. Ice is an example of the crystalline. It's really organized, right? And we have what we call amorphous. A means lack. Morph means shape. So lack of shape. So it's not organized, in other words, okay? So this is basically showing you everything that I just talked about. A nice, beautiful model, right? So gas, you guys cook, right?
Yes.
Yes.
Are you guys good at boiling water?
Yeah.
Yeah? Well, I'm horrible at it because I always forget that I'm boiling water, right? And so by the time I get back to the kitchen, my kitchen is filled with steam because I just boiled off all of the water that I was going to use for my pasta, right? Or my cup of noodle, depending on what day it is, right? So I'm a bachelor, so I eat a lot of cup of noodles, okay? Don't make fun of me. Anytime you want to change that, you can cook me a meal, okay? So steam is going to occupy what you allow it to occupy. It'll be able to occupy the entire room, okay? So where water is going to be limited by the container, right? And ice, well, we got the ice tray. After you dump the ice out of the ice tray, it's going to keep it there as long as it's cold enough, and it's going to be that nice little square, or like I have heart-shaped ice trays, right? So each of my ice trays is a little bit of a heart. I'm a Valentine's baby, so I get a lot of heart stuff, so. Okay, questions, concerns, cash? Pretty simple so far, right? Oh, you're saying you have no cash? I accept cash. Okay, so this is just showing you that this is a physical property, right? And the only thing that we're doing differently between the ice, the liquid, and the gas is that we're changing that temperature. And as a result of that, we get a physical change. Okay. Okay, so let's talk about chemical changes. So a chemical change, or like we like to talk about it, chemical reactions, are basically when you start off with one molecule or a couple of molecules and you change the arrangement of those molecules, or you break them down into their components, okay? So again, I like to try to cook every once in a while when I'm really trying to be fancy. So I've tried to make caramels, right? This is not my pictures. I'd love to take credit for this because there's this nice, controlled and organized. Mine was not controlled and organized. Things were on fire and things like that was happening in my kitchen at that point. Again, because I was trying to do multitask. You know, I'm a great multitasker. That's what I tell myself, right? So I got my sugar and I started melting my sugar. Heating it slowly, it was looking beautiful. I'm like, okay, it's melting. I'm just gonna go and, you know, grate a couple of papers and things like that. And as I grate, I drink a little bit, and then I forgot totally about my caramels, right? I come back and the room is all smoky. There's fires coming here because of the sugar boiling out, and the sugar boiling out here and everything like that, and everything is black, pitch black. And I'm gonna ask you one question. Can I get that sugar back?
No.
That I just burned to a crisp, right? So that's typically a sign of a chemical reaction because you can't get what you got originally. Like with water, if we cool it down or freeze it, we can make it back into ice. Can we not?
Yes.
Or if we condensate it, collect it from off the walls, you know, it'll sit there and condensate and we'll get water dripping off the walls, right? So physical reaction, you're going to be able to get what you lost or collect what you lost in some way or another. Where a chemical reaction, you're going to get two totally different components. In this case, you're going to get ash and water, right? Or coal and water. So carbon is just a form of coal. Okay, so this is a chemical reaction. Here's the name of the chemical components. This is sucrose. This is the chemical formula for sucrose. Now you'll notice we have C12. That means that I have 12 carbons in this molecule. I have 22 hydrogens and I have 11 oxygens. okay? This side is called my reactant. In this case, we only have one reactant. This side is called the products. Here I have two products. Oops. Sorry. I had to give myself enough room to write. Okay, so this means that we have one sucrose molecule, right? Now, we always set up a chemical reaction the simplest way possible, right? We don't take into account every molecule of sugar here at this point. We just talk about one single molecule or a couple of molecules for a reaction. Simplest form, okay? So we have one sucrose molecule, and that's gonna make, so this is gonna change into, this line means change into or make or generate, okay, or yield 12 carbon atoms and 11 water compounds, okay? You guys got that? I think Vanessa froze on me. You got it, Carla?
Yes.
Yeah, okay. So this is considered to be a balanced chemical equation. Now, the reason why it's considered to be balanced is because what we started with, what you put in, is what you got out. This here is called the law of conservation. What you put in is what you must get out. Chemistry is based upon the law of conservation of matter, okay? Now, another way of saying that is chemicals aren't made or generated. They're just converted or rearranged, okay? Because if you look at this, how many carbon do I have over here?
12.
12.
Okay, so I have 12 over here on the reactant side. And then how many do I have on the product side?
12.
How many oxygens do I have on the reactant side?
11.
2.
And then on the product side?
1.
2.
Oh, no, 11.
11.
11.
Oh, yeah, 11.
11.
Yep. And these are called coefficients. Your coefficients, they tell you how many you have of that whole entire molecule. So that means you have 11 oxygens. And then hydrogens, how many hydrogens do I have on the reactant side?
22.
22.
22. And then how many do I have on the product side?
22.
2.
Okay, so that tells me that I'm balanced, right? And I put in what I put in, I got out of my chemical reaction, okay? So it meets the check mark saying that we've gone through the law of conservation. Piece of cake? Good. Okay, so because we broke down these compounds, this is a chemical change. We can't recover back, we can't get sucrose back from the stuff that we have, right? Do you guys see that? Okay, so we've talked about physical reactions and chemical reactions. Now, I want you to tell me in a poll. The first one, A, is it a physical or a chemical reaction, or both? Log burning. Now, there's only 12 of you, so all of you guys should vote. Come on, I know I got more than 50%.
I think it's both. Both.
Okay, so click both on your poll. A poll should have popped up. We're almost there. 2 more. One more. Okay, 100%. Let's see what you guys said. Okay, so the correct answer is it's a chemical reaction. Because at the end of it, what are you going to get?
Professor, what did you say?
I said it's a chemical reaction.
Oh,
I said at
okay.
the end of the reaction, what are you going to get? After you burn that log, are you able to get that log back?
No.
No.
No, it's one and done, right? Once you burn it, that's it. You're not burning it again, right? So all you have left is ash, right? Okay, what about water melting? I mean, sorry, ice melting, not water melting. Okay. One more person. Ice melting. Put your vote in. There we go. Okay, so the correct answer is physical. It is a physical reaction. Because if we freeze it, we're going to be able to get it back, won't we?
Yes.
Okay. Okay, so the last one, glow sticks. You bust open that glow stick, you shake it. So, physical or chemical? Or both? Come on, 3 more. We're almost there.
Professor,
Yes,
what do we shake?
the glow stick, because you have to shake it to get it to mix. And then you dance with it all night. One more. Come on. Don't be shy. Okay, chemical reaction is the correct answer. Right. So there's a chemical inside the middle of the glow stick. On the outside, there's water. So when you break, it reacts with the water and causes it to glow. And then that glow happens for so long, 2 hours, 8 hours, depends on if you got the really good glow sticks or you got the glow sticks at the dollar store, right? So. Piece of cake so far? Good. Okay, pure, damn it, I did it again. So pure substances. So pure substances is made up of a single thing. Okay, so I'm gonna ask you, sucrose, pure cane sugar, right? Because table sugar is sucrose. CNH sugar, you guys heard of CNH sugar? CNH, pure cane sugar from Hawaii. Okay, so none of you guys go shopping, okay? Or listen to commercials in the 80s. So, sugar. Do you guys think sugar is a pure substance or is it a mixture?
A mixture.
I think it's pure.
How many of you guys think it's pure? Raise your hand. Yeah. So sugar is pure, right? It's, again, the chemical formula is C12H22O11. So that's pure sugar, okay? So a pure substance can be made up of multiple atoms, right? It has 3 atoms that it's made up of, but it's a pure substance. It's a pure compound, okay? So elements or compounds or molecules can be pure, okay? A mixture is when you're mixing 2 different chemicals and they're not reacting with each other. You want me to give you an example? So how about salt and sugar, right? Have you guys ever been to a diner?
Yes.
You know, I'm just asking because sometimes it's rare. You know, some people, it's rare, I know, but some people don't go to diners. Okay, so you know where they have the little sugar container that you can use to put in your coffee? So as a kid, what I used to do, I would take the salt and dump it in the sugar container, and I'd mix it up, right? Now, looking at it, can you tell the difference between sugar and salt? Now, what do you think they did when they put in their coffee? Goddamn kids. No. You know? So they were a little upset. They're like, hey, what the hell's going on here? Right? My coffee is now salty. These damn kids. Right? I was one of those kids. Right? But never got caught. Anyway. So that's an example of a mixture. Is it not? Sugar, salt. Right? So there are 2 types of mixture. Like I said, could you tell it apart visually? Could you sit and say, oh yeah, that's a sugar molecule. Oh no, that's a salt molecule. Could you do that with your eyes? No, you can't, right? So that mixture there is called homogeneous or homogeneous, okay? You heard of homogeneous milk? Right? It's called homogeneous because it's all blended together, so it's all nice and clear, right? Fresh milk, if you let it sit long enough, it'll actually settle and you'll see differences, right? So if it's not homogeneous and you can tell the difference, like let's say salt and pepper. So if I mix salt and pepper together, can I tell the difference between them? Yeah, I can visually tell the difference. One's black, one's white, all right? So what do you think that's going to be called?
Heterogeneous.
Heterogeneous. Okay, homogeneous means uniform throughout the entire thing. Okay. And that's putting it simply. Okay, questions, concerns, Cash? Okay, good. Okay, so how many of you guys cook pasta? Okay, only one of you guys cook pasta, that's it?
I do.
2, I got 2 who cooks. Nobody else cook? Kevin, you don't cook?
No.
No. Oh, okay, you got a girlfriend or a mom, huh? Or a boyfriend? Those who cook pasta, why do you add salt?
To give it flavor.
To give it flavor?
Don't they also say that it makes it boil faster or something?
Oh, so it doesn't boil over.
So it doesn't boil over, it boils faster. Anybody else? Bernardo, why do you add salt to your pasta?
I don't know.
You don't know?
Either.
You don't cook? Brian, what do you think?
Oh, I don't put salt. I don't know.
You don't put salt in your pasta?
No.
Okay. Okay. So you put salt in your pasta. Well, everybody says, oh, yeah, for the salt. But you could put salt on it afterwards, right? Or in most cases, there's enough salt in the spaghetti sauce afterwards to kind of cover it. So you don't need it for flavor, right? So the reason why we put salt in pasta for two reasons. One, if you take a look at this, this is the case with water with salt. So water boils at 100 degrees Celsius. So it's not that it actually boils faster, right? It's just the fact that if you have salt there, it allows it to actually start boiling at a higher temperature. So who said it to keep it from boiling over? That is technically correct. So we put salt in there to kind of keep it from boiling over. And also so that we can get the water hot enough that it cooks the pasta fast. Because nobody likes soft and gushy pasta, right? You guys don't like soft and gushy pasta?
Nope.
Mushy pasta, right? So you want to sit there and get it nice and hot and then throw your pasta in and cook it pretty fast, right? And plus, usually if you're cooking pasta, you're pretty damn hungry in the first place because that's why you're cooking pasta, something quick, right? Okay, so it changes the boiling point, okay? So now we talked about changing the boiling point, us adding salt to water, okay? So is that a physical change or is that a chemical change?
Physical?
That is correct. The change in boiling point or the change in freezing point is considered to be a physical change. Okay? Okay, so let's talk a little bit more about mixtures. Okay, so if I have pure bromine and I have pure water, and I mix the bromine and the water together. Here I just put a little bit of bromine in the water. It's all uniform throughout. It's got a nice little light brown color to it, right? Now we look at it. We didn't make a chemical change because the bromine and the water are not reacting with each other. Water molecules, the Mickey Mouse ears, right? So oxygen has a red color, the hydrogens are white, so the two hydrogens, the one oxygen. So, and the bromine here, bromine is a diatomic molecule. We'll talk about diatomics in a second. But bromine, right, is right here, much bigger than the water molecule, right? And there's only a few of them in this mixture. Now, if we add a whole bunch of bromine to the water, it makes it a little bit darker, not as dark as the bromine that's pure, but a little bit darker, right? And it's a mixture again. We're not getting a chemical reaction. So these are two independent things that are interacting in the same space. It's kind of like, how many of you guys have friends, just friends? You're not couples. You know what I'm saying? Okay. And then how many of you guys have friends, right? As in, ooh, baby, we hook up every once in a while, friends, you know? We kiss every once in a while, friends. You guys have friends like that before, right? Yeah, okay. So we're all adults. We have adult relationships, right? So similar to that, right? So the friends that hook up every once in a while, that's kind of like a chemical reaction. We're just friends, is you guys are existing in the same space, right? You both go home to your own places and all that stuff. You don't do the nasty, you know, where in the case of the one that you're my friend, right, you do the nasty. So that's an example of a chemical reaction versus, you know, independent, inert type of things, okay? Inert meaning not reacting. And I'll spell it for you. So I should say, are your friends inert? Or is there a little bit of chemistry going on there? Okay. Okay. So homogeneous mixtures are considered to be a solution. Okay. And where they're pretty much the same size and everything like that. Heterologous mixtures, they're considered to be phase differences associated with it. So like for instance, if I have salt or a whole bunch of salt and water that isn't dissolved, right? The salt molecules at the bottom, that's two different phases. We have one in the solid and we have some that's going to be in a liquid, okay? Or sand and water. That's probably a better example, okay? So how many of you guys drink alcohol? So how many of you guys turn up? So my family drinks a lot and they would always drink me under the table. And after I go out drinking with them, I would always be sick and I hate being sick. I hate it. It's something I really despise. So what I learned is I go and buy the drinks when I go out with my family, right? And so I tell the bartender, I said, okay, I want you to water down my drink. So then they think I'm drinking as much as they are, right? And then I get to go home and not be sick, right? So can you tell the difference between, say, a cocktail that's been watered down compared to a cocktail that hasn't?
Yes.
Other than drinking it. Visually, can you tell the difference?
I mean, maybe if the color kind of fades, but other than that, not really.
Yeah, so I mean, you'd have to really be looking to say, okay, that's a little lighter than, let's say I'm having rum and Coke. If he puts the rum, just half the rum he normally puts in water, you're not going to be able to tell the difference because the Coke covers the color, right? So is that rum and Coke a homogeneous mixture, or is it a heterogeneous mixture?
Heterogeneous?
Homogeneous.
Is it heterogeneous, rum and Coke?
Homogeneous because you can't really tell the difference. So kind of like the same.
Oh, okay.
Yep. So it's uniform throughout the entire thing. It looks throughout exactly the same throughout, right? Piece of cake? So this is just basically showing you that. Here we have pure water. Here we have pure ethanol. Ethanol is drinking alcohol. And if I mix the two, can you tell the difference? But if we looked at them at a molecular level or at a particulate level, you can tell the difference, right, between the water molecule and the alcohol molecule. Okay? Here's the question. Don't worry about it, Vanessa. It happens to the best of us, you know.
Thank you.
Okay, so, oops, got carried away. So now, when you're making alcohol, any of you guys are bootleggers? Make alcohol in your basement or in your garage or in your kitchen? No bootleggers? Well, I am. I like to make beer and wine, right? And next year I'm going to be making some brandy, right? So brandy is, do you guys know what brandy is?
Yes.
Yes. What is brandy? Well, I can tell you what brandy is. So brandy is fruit wine that has been concentrated. So it's high in alcohol. So how do you think I go from going from wine to brandy? Take a guess. You guys are young budding chemists.
By not letting it sit.
By not letting it what?
By not letting it sit as much.
By not letting it sit as much. No. You can let it sit as much. So typically when you make wine, wine is made through fermentation, adding yeast and sugar. And typically the yeast breaks down the sugar to make ethanol, drinking alcohol. It also makes carbon dioxide. Now, if you let it sit long enough, it'll use up all of the sugar that's there and it will make alcohol. But there's a point where it'll stop making alcohol. And that's the point where it starts killing the yeast. So the alcohol basically will kill, too much of alcohol will kill you, and it would also kill yeast. So for yeast, their drinking point is roughly 20% per yeast. Wild yeast is probably 12%. Specialized yeast or brewing yeast, it's about 20, 23%. So the most that you can get is 23% alcohol in your solution. So if you can only get 23% alcohol in your solution, how do I get it? Brandy is typically 40, 50% alcohol. How do I go from 20% to 40 or 50% alcohol? What do you guys think?
Do you add more sugar?
Add more sugar? Well, if you add more sugar, the yeast are still going to die at 20%. That's the most I can get. Any other suggestions?
You add more ethanol?
We're making ethanol by fermentation, so we're not going to be adding more ethanol. No, we're still at 20%. That's the most that we can get. We're not fortifying it. What do you guys think?
Bigger amount of wine.
A bigger amount of wine? Well, regardless of how much wine I could have, like for instance, right now I have 23 5-gallon jugs of wine being made all together. So I could have 103. It's still going to give me 20% alcohol in each one of those. So how do I make it go from 20% to 40%?
You have to add more fruit to it?
No, not more fruit. Fruit ain't going to help it either.
Add more yeast.
No more, not more yeast. Okay, so we're going, let's think about this, and I want you to think about it. We're going from 20% to 40%. Even if I add more yeast, the yeast are all going to die at 20%. Have you guys heard of distillation?
Oh, okay.
Okay. So distillation is the process of using temperature to separate alcohol, in this case, alcohol from water, right? So 80% of it is water, and 20% of it is alcohol. So the way I get rid of the water is either I could boil off the water or I could boil off the alcohol, right? So alcohol boils at 87.9 degrees Celsius. And water boils at 100 degrees Celsius. Can I separate those two? The alcohol from the water?
Yes.
How?
Through distillation.
Through distillation. So how would I do it? Tell me the procedure.
You boil it off and then it catches in another like container, like the water, because it turns into a vapor, right?
So is it the water that's going to be turning into a vapor, or is it going to be the alcohol turning into
the water? The water.
Are you sure? Which one is going to boil first? This is alcohol, boils here.
The alcohol.
Oh yeah, the alcohol, because it boils at a lower temperature.
That's right. Yeah, so you have one component that's going to boil at a different temperature than the other. So the one that's boiling at a lower temperature, it's going to turn into a vapor. Then what's going to happen is that the vapor is going to go up. You're going to have another tube that's going to condense that vapor so that it becomes a liquid again, okay? So we have a cooling tube. And so you cool it down, and then you collect the alcohol. So I can go, literally, I can go from 20% to 100% alcohol if I'm good, or 80% alcohol, depending on my distillation system, okay? Now, don't try this at home because it blows up places. Don't do it right, okay? So, and the key is that you want to get a temperature that is slightly above the boiling point of alcohol, just a little bit above it, but not so high that it's 100 degrees Celsius, so you're keeping the water there. Otherwise, you're going to be boiling the water and the alcohol, which you don't want to do. Okay? Questions? Concerns? Okay, so now The whole purpose of me talking about distillation is, are we using a physical change? Or are we using a chemical change?
Physical.
To sit there and separate the two. Physical, that is correct. We are using a physical change for separation. Okay, so here I have a mixture of iron and sulfur. So iron, we know, is magnetic. Sulfur, iron is also a metal. Sulfur isn't magnetic. Sulfur is a non-metal. Now, I can separate the sulfur from the iron by just swiping over a magnet. Make sense? So is that a physical reaction or a chemical reaction?
Sir, please can you say that again? I didn't hear that.
I can separate the iron from the sulfur, right? If I have a mixture of iron and sulfur, I can separate the iron from the sulfur by swiping a magnet over it, right? By putting a magnet in there, right? So the iron's going to bind to the magnet, the sulfur is going to stay there, right? And you guys can see that happening here. Okay, so what does that mean? Is it a physical reaction or is this a chemical reaction?
Chemical?
Is it?
Well, I was just thinking, like, if the magnet's picking up the iron, then.
Like, but are we changing the iron in any way?
No.
No. So is it a physical reaction or is it a chemical reaction?
Physical.
Physical. So we're using a characteristic of the iron. We know that it's magnetic. It binds to a magnet, right? And if we pull it off the magnet, it's still going to be iron, right? Okay, so we can use those physical properties to separate two compounds or two elements or two molecules, okay? We can use distillation. We could use filtration. Filtration is separating liquids from solids by using a filter paper. How many of you guys drink coffee? Coffee. Okay, so do you guys have grinds in your coffee when you drink it? You do? Or you use filter paper to sit there and filter it out?
Nothing. My Keurig is just broken, so that's why I have grounds in my coffee. But normally you shouldn't because you use a filter. Okay, so if you're using a filter, or you can use a little Keurig and then put a little filter at the bottom, right? Mm-hmm. And then if you do that, then you're not collecting the grinds, right? And so then you're able to separate your liquid from a solid, right? So that's the same thing that happens with filtration in terms of. So here, this is a distillation column. Again, you're boiling the liquid, you're separating the two, one at a certain boiling point. The vapor goes up. This is a cooling tube. The cooling tube has liquid on the outside, and then the vapor's going down this tube and it's being cooled. So then you get condensation. So then you're able to collect your pure substance. This here is an example of gravitational filtration. So we're using gravity to separate a solid and a liquid. So we have a mixture of a liquid and solid here. We pour it in here with filter paper. We fold up our filter paper in a nice little manner. And then as we pour it through, gravity pushes down on the liquid. Liquid flows through, and we get the pure liquid at the bottom, and we collect the solid up top. Okay, so elements, compounds, and molecules. Okay, so an element is a pure substance that can't be broken down to anything else. So they're also going to be the things that you see on your periodic table. Have you guys seen the periodic table?
Yes.
Okay, so if you guys go to P table, here's your periodic table. What was that, Alberto?
I have a question. What's an example of like separating two mixtures with like a chemical reaction?
What is an example of separating two mixtures with a chemical reaction?
Yeah.
There isn't an example. So you usually use, if you're trying to separate two mixtures that are together, you're going to use a physical reaction. You're not going to use chemical reaction, because then you're not going to get those two mixtures, those two pure components independently. You're going to get something that's not the same.
Okay.
Okay. Okay, so this is your periodic table, right? There's a couple things that I want to talk to you about your periodic table real quick before we go back to elements, molecules, chemicals. So each of these are considered to be an atom. Atom is considered to be the smallest unit, smallest functioning unit of an element. Okay, so atoms themselves are made up of 3 parts, or subatomic particles. And we'll talk about this again, I promise. We have the proton, which is a positively charged particle. We have the electron, which is a negatively charged particle. And then we have the neutron. So what do you guys think the neutron is? What do you think the neutron is? Brian? So if a proton is positively charged and an electron is negatively charged, what do you think a neutron is? Are you there? What was that, Bernardo?
Neutral.
Neutral. Okay. So the way an atom is set up is, now you have to excuse my horrible drawings. So in the center, we have that little red dot represents, this is where your protons and your neutrons are going to be. Out here orbiting, kind of like how the Earth orbits the sun, are your electrons, okay? And they have different orbits that they do. We'll talk about that later. But for right now, just getting the concept of electrons are on the outside, protons and neutrons are in the middle. Okay? You guys are good so far? Piece of cake? Okay, so your atomic number, this number right here. Can I erase my little diagram of my... My atomic number represents the number of protons. Okay, so hydrogen is always going to have 1 proton. That's going to define what hydrogen is. Hydrogen is always going to have 1 proton, okay? So how many protons does silicon have? What is the chemical symbol for silicon first?
Si.
Si. So how many protons does silicon have?
14.
14. What is the atomic number for silicon?
14.
14. Okay. Now, every atom on your periodic table, for it to be in its natural state and to be an element, right, it has to have the same number of electrons as you have protons. Okay. It has to be neutral, neutrally charged. So electrons are positive. Electrons are negative, protons are positive. Okay. So how many electrons does hydrogen have?
14.
Hydrogen.
1.
How many electrons does hydrogen have?
1.
1. That's right. So because it has 1 proton, it has to have 1 electron. Okay. So that is when it's an element. Okay. An element, or it's an atom. Now, when it's an ion, it'll be different. But for right now, we're not talking about ions. Okay. So how many electrons does magnesium metal have?
12.
12. Okay. Piece of cake so far? Okay, so let's make it a little more challenging. Okay, so your electrons, they're so light. They are so light. It's kind of like, so I weigh 220 pounds. If I have a speck of dust on my shoulder, is my weight going to change?
No.
No, it's not going to change. So the electrons are so light, they're kind of like that speck of dust on the protons and the neutrons' shoulder. So your mass, your atomic mass or your atomic weight is made up of the weight of your protons and your neutrons, okay? So atomic mass is this, okay? So, but let me kind of explain this in a little more detail. Our mass number is going to equal to the whole number of the atomic mass. You guys know what I mean by a whole number?
Yes.
What do I mean?
Like 10, 20.
Okay. So if it's 1.008, what would be the whole number of that?
2.
It would be 2?
It's 1.
Wait, 1.
1? Okay. So what is the mass number for vanadium?
51.
51. Okay. Okay. So what we can also say is the mass number is also equal to the number of protons plus the number of neutrons. Okay. Really running out of room now, huh? So mass number is equal to the number of protons and neutrons. Okay. So hydrogen. What is the mass number of hydrogen?
1.
1. How many protons does hydrogen have?
1.
How many neutrons does hydrogen have?
0.
That's correct. 0. Yeah. Okay. So
I have a question. Why is it 0?
because the mass number is going to be 1.
Mm-hmm.
1 equals to 1 plus what? What does it have to be?
1.
So 1 is equal to 1 plus, and that's my number of neutrons. What does my number of neutrons have to be if it's equal to 1?
Is it 1?
Negative.
Negative?
It's just 0.
0.
0.
0, right? Because 0 plus 1 equals 1, doesn't it?
Mm-hmm.
Because if I said it was 1, I'd get 1 plus 1 equals 1. Is that true?
No.
No. And if I said negative, that would give me 0 over here, and that's 1. That wouldn't be true either, right? And plus, you can't have a negative neutron, you know. Okay? So, you guys get that? So we can say the mass number minus the number of protons is going to equal my number of neutrons. Okay?
So I don't get that, Professor.
Mass number, you don't get it?
Yeah.
So mass number is equal to the number of protons plus the number of neutrons, right?
Okay.
Okay, so number of protons is given to me by my atomic number, which is 1, right? So my mass number, which is this rounded, which is going to be 1. So I have 1 here, and I have 1 here. So this number has to be what?
0.
0, yeah.
Because
So we're saying 1 is equal to 1 plus
0.
x. So what is x? X has to be what?
0.
0, right? Because if we solve this for x, x is equal to 0.
Oh, okay. I didn't know that it was kind of like a math problem. I just thought that like some people just knew that it was 0, and I was like, how do you just know that it's 0?
No, you just subtracted, right?
Yeah.
You see that?
That was the part that I was confused about. I didn't know that it was like an actual like math problem.
Do you see that now?
Yes.
Yeah.
I do.
What about, I'm going to butcher it again.
Rocky. My first name is Rocky.
Rocky. Yeah, Rocky.
Yeah.
Yes. Do you get it, Rocky?
Yes, I got it now.
Yeah. Okay, good. Okay, so now that you got all that information, and is it seeping in? Okay, let's test it out. So tell me the chemical symbol for mobidium. Can I erase all of this? You guys got this written down so we can make a little more room to work? Mobidium. We're looking for a mobidium. What is the chemical symbol for mobidium?
MO.
MO, mo. Okay. MO. Okay. So how many electrons does MO have?
42.
So electrons. The E minus represents electrons. Okay, so we have 42. Okay, how many protons? The P plus means protons.
42.
What is its atomic number?
96.
84.
42.
42. That is correct. What is atomic mass?
54.
96.
Are you sure?
84.
What was that? Its atomic mass.
95.95.
95.95. Because the atomic mass is what's written up here, right? Now, what is its atomic, its mass number? Sorry, mass number.
96.
Yes, 96. Mass number is 96. Okay, and the number of neutrons?
54.
And how did you calculate that?
It's mass number minus number of protons, right?
That's right. Piece of cake? Yeah, that look. I'm getting, what does that mean? You guys get it? You want to try one more? One more for the road?
Yeah.
Okay, so let's do gold. What is the chemical symbol for gold?
AU.
Okay, AU. What is it? Its atomic number?
$79.
Okay. What is its atomic mass?
$196.97.
So 196.97. Okay. What is its number of protons?
79.
Its number of electrons?
196.97.
Nope.
79.
79.
Oh, yeah, okay.
Number of neutrons?
118.
Okay. Piece of cake? What do you think, Katrina? I mean, Karina, not to put a T in there. Karina?
I'm barely catching up. P.
That P plus means protons. It's a little P plus.
I'm sorry, I'm still a little confused.
Okay, what part?
I'm still.
So again, atomic number is equal to the number of protons. So that tells me how many positive charges I have, right? So I know because it's an element, it's going to have the same number of positive charges as negative charges. So its atomic number for a goal, so my goal is 79. So I have 79 positive charges. That means I must have how many negative charges, Katrina?
79.
Oh, Katrina. Oh, I did. I said Katrina. I got it right. 79. Okay. So that tells me about the positive and negative charges. And then what is its atomic mass?
196.97.
196.97. What's the whole number for 196.97?
197.
197. So 197 is going to be equal to the number of protons plus the number of neutrons. So if this is 79 and this is 197, the mass number is 197. So 79 197 minus 79 is going to equal my number of neutrons, which is
118.
Okay. So does that make sense?
Yes.
Okay. Piece of cake. You guys have that look. I'm getting so many different looks going on here. Yeah, no, Rocky?
Got it.
You got it?
I'm trying to learn how you got the answers. So,
this here, this is our mass number, right? We get our mass number by the whole number of the atomic mass. So goal, atomic mass, right here.
mm-hmm.
So what is the whole number of 196.97?
That would be 197.
197. So 197, and we know that the mass number is equal to the number of protons plus the number of neutrons. So if I take my mass number and I subtract the number of protons, that's going to give me my number of neutrons. Okay?
Okay.
Yeah, so that's just changing, you know, a little bit of algebra. So 197 minus 79, because that's the atomic number, which is also the number of protons, that's going to equal 118. And that's going to give me my number of neutrons.
Okay.
You got it?
Got it.
Okay. Okay, so just to make me happy, can you do one more for me? Let's do nitrogen.
Which one do you want us to do? I didn't hear that.
Nitrogen?
Nitrogen.
Nitrogen, yeah. So what is the chemical symbol for nitrogen?
7. N?
Chemical N, okay. And now, what is the atomic number for nitrogen?
7.
Okay, so atomic number is 7. Okay, number of protons?
7.
Number of electrons?
7.
Number, atomic mass?
14.
14.
I can't read that.
14.007.
14.
Okay. Yeah. Okay, atomic number?
14.
7.
Oh yeah. Sorry, I thought you said atomic mass. Or...
I did say atomic mass, and then I said mass number. Mass number was, you said 14. That's correct.
So was I wrong? I'm kind of confused now.
No, you're correct.
Oh, okay.
They were just jumping ahead and tell me the number of neutrons.
Oh, okay.
Number of neutrons?
7.
They're not letting me write anything down, you know. They're like, come on, hurry up. I'm ready to go. So 7, 7, and 7, right?
Yeah, I think the problem before why I wasn't getting it was like you would ask us, okay, like what's the number for this one, and then I would have to look over like the entire table to try to find it, and by the time that I found it, like you were so far ahead that I was like, wait, I'm like so lost now. So
yeah. But now you got it now? Everybody got it now?
Yeah. And also the language is kind of confusing because it sounds so similar to like
atomic mass, atomic number, atomic mass number.
Okay. Yeah. All right. Atomic number.
Yes. Yes.
Atomic number.
So I just like need to go step by step is the thing.
Okay.
Yeah.
Okay, pretty good so far?
Mass. So, Professor, the mass number is the one you round off, right?
That's right.
Oh.
Will the atomic number, proton, and electrons always be the same number?
So will the atomic number, protons, and electrons, not always. So there will be cases where you have what we call ions. Ions are basically either you're gaining electrons or you're losing electrons.
Through a compound, right?
Not necessarily through a compound. You're going to be exchanging. So one is going to give it up and somebody else is going to pick it. We'll talk about that later. Yeah.
I meant like by itself though.
By itself, alone, no. It's always going to be, if it's an element by itself, it's always going to have the same number of electrons as you have protons.
Protons.
Yes.
Which is essentially the atomic, well.
The atomic number, yes.
Yeah. Okay, so not until we actually add another. Okay, got it.
Yep, okay. So, everybody got that so far?
Yes.
Okay, good. So I'm going to erase my board here and we're going to continue talking about our periodic table because I have a few more things to go over. Okay, so we have what we call diatomic elements. Every other element, when it's by itself, except for, there's two other ones that are kind of special. Every other element, when it's by itself, it's only by itself. Like sodium, right? We're talking about sodium metal. We'd only have one sodium metal. Now, these elements are considered to be diatomic because in nature, meaning in the real world, they have to be paired up with themselves. The ones that are diatomic, the way I remember the ones that are diatomic, there's 7 of them, right? It's have, no fear of ice cold beer. Okay, have no fear of ice cold beer. Okay, hydrogen, nitrogen,
phosphorus,
fluorine, oxygen, iodine, chlorine, and bromine. So these guys will always be diatomic, meaning there will be 2 atoms of hydrogen, 2 atoms of nitrogen, 2 atoms of fluorine, or 2 atoms of oxygen when they're alone by themselves. So they don't like being alone, in other words. So anytime that they're by themselves in a chemical reaction, then you're going to make sure that you have H2 if we're talking about hydrogen. Or if we're talking about nitrogen, we're going to have N2. Okay, so this guy is not alone. It's with, this is carbon monoxide. So we don't have to have a 2 when it's with somebody, only when it's all by itself. Okay. So oxygen gas is always going to be O2. Hydrogen gas is always going to be H2. Nitrogen gas is always going to be N2. Fluorine is always going to be F2. Okay. Did you guys get that?
Yes.
Okay. Okay, so you guys ready to go back? Since we talked about that. Now, that helps us with our definitions. Okay, so that helps us with our definitions, right? So I had molecules down here. So a molecule is 2 or more atoms. Very general, right? Okay, a compound, it's also defined as 2 or more different atoms. Okay.
Wait, so what is two or more different atoms?
A compound.
Oh, okay.
Okay, so okay, and then element. An element is the simplest form, right? So for instance, H2 is considered an element because it's only hydrogen. Na. So here's an example of an element, or so these are two examples of elements. This is a compound. And these are examples of molecules. Okay? You guys got it? Yeah, no, maybe?
Yes.
Okay, so let's test this out. Okay, O2, element, compound, or molecule?
Molecule.
Okay. I'm just going to use M for short, since I'm being lazy. Okay. Is it an element?
Yes.
Okay. So it's a molecule and an element. What about NO?
Compound? Or
Compound.
no, a molecule.
It's a compound.
Yeah, and it's a molecule.
And it's a molecule.
Mm-hmm.
Okay, what about zinc?
An element.
Piece of cake?
Mm-hmm.
Everyone get it?
I'm not getting it, please.
You're not getting it?
Yes.
Okay, so the definition of a molecule means two or more atoms. Okay, O2, how many atoms do I have there?
2.
You have to.
Okay, so that means it's a molecule, right?
Yeah.
Okay, a compound says it is two or more different atoms. Is O2 two or more different atoms?
No.
Nope, so it's not a compound.
Mm-hmm.
Okay, element. We know, we just talked about it being diatomic element. Anytime you see it by itself and it has two there, it's a diatomic element. It's an element. Okay, so it's an element and a molecule. NO. So is there two or more atoms for NO?
Yes.
Yes.
Yes, because there's an N and there's an O. Okay, what about compound? Compound is two or more different atoms.
Okay.
N and an O. Okay, and then, so that means it's a compound and a molecule.
Mm-hmm.
Okay, the last one, zinc. Is it a molecule? Is it two or more? Zinc.
I think it's element.
It is an element. That's right. Yep.
I have a question. What's the difference between a molecule and a compound? Because I can't tell by the definitions that you put down there, like what's so different about them.
Molecule is 2 or more atoms.
Mm-hmm.
It doesn't say different, right? All you need is 2 or more, right? Oxygen is 2 or more. So, for instance, oxygen can be a molecule, right? But it can't be a compound because it's not 2 or more different atoms.
Okay.
Okay, so that is the difference. The difference.
Okay,
you see
and
the
then
difference?
Yeah, and then molecule can be same or different.
That's right.
Okay.
As long as there's 2 or more, right?
Okay, gotcha.
Right? 2 of them. Piece of cake?
Mm-hmm.
Okay, so pure substances can be elements and they can also be compounds. So you can break things down into elements and to compounds, right? You can separate mixtures that were elements and compounds.
So the only molecules are the seven elements that go together?
No. CO is a molecule, right? Because the rule for a molecule is all it has to have is at least 2 atoms. They could be the same or they could be different. It doesn't matter, right? So sulfur is a polyatomic. It has 8, right? That's its natural state. So is that a molecule?
Yes.
Is it an element?
Yes.
Is it a compound?
No.
Okay, that's right. So, piece of cake?
Yes.
Okay. Okay, can I erase? You guys got it? Okay, so mixtures, right, also means impure, right? Mixtures, they can be separated by physical means. So then you can get compounds, pure compounds, or you can get elements, depending on what your mixture is, okay? So compounds, a pure compound, can only be separated by chemical means. And then by doing chemical means, you can get your element back, all your elements back, or you can get compounds, pure compounds back, or you can get a combination of both, okay? So these are examples of pure substances like your pencil lead, which is just graphite. The pre-1982 penny was pure copper. Your iron bolts, right? A long time ago, silicone wafers, right? And then your lead weights, copper wire, your 24 karat gold bracelet. Now these are examples of compounds. Baking soda, let's see, Rolaids are fixation solutions. So we experience a lot of these throughout life, right? So you're going to experience things that are going to be pure, and then also things that are going to be, well, elements, and things that are also going to be compounds, okay? So we've talked about the symbols on the periodic table. So you could either have, on your periodic table, we have cases where we have just a single letter, but there's also other cases where it's a double letter, okay? So helium is He, okay? So it's going to be important that you write your chemical formula correctly. You want to write sodium as Na, because if you write it as Na, I won't know what you're talking about, okay? Or it can mean something else, right? So like if I write this as in lowercase o, and I'm talking about nitrogen and oxygen, then I'm going to say this is nobidium, right? Which is NO, okay? instead of writing it as N capital O. So you want to be sure you write the correct chemical formula. Questions? Concerns?
No.
Okay. So we've talked about a molecule, we've talked about an atom. So the law of constant composition basically says that when we write our chemical formulas, H2O, or let me give you another example, CO versus CO2. So carbon monoxide is different than carbon dioxide. They're going to behave differently. They're not exactly the same, but they're going to have that ratio carbon to oxygen, right? So that's going to be a 1-to-1 ratio. So its mass is also going to be proportional to each other in some way. Carbon weighs 12, oxygen weighs 16. Where in this case, we have 1 carbon, 2 oxygen. So that's going to be a ratio of carbon to our 2 oxygens, right? In terms of mass. So the law of definite composition basically means that that ratio is going to be fixed. It's not going to change, regardless of how much of it you have. You could have a pound of carbon, it's still going to have that ratio of 1 carbon to 2 oxygens. Okay? We've talked about those charges, and also just the fact that a lot of chemical compounds are based upon charges themselves, right? So it deals with electrostatic charges. Electrostatic charges are just basically electric forces. Have you guys ever wore your socks and then went around the carpet and just rub your feet on the ground and then go to your brother or sister and poke them?
Pop them.
Right? So that is just building up that electrostatic charge, right? So it's that negative charge, and then you're sending it to your brother or sister and gives them a little, and they're like, what the hell did you do that for, right? So that's an example of that. Okay, so because you have these charges and we can generate them by rubbing our feet and things like that, because the electrons that are being able to be transferred, we can get positive and negative charges on things. And we know that 2 charges are going to be exactly the same. What's going to happen if we have 2 positive charges?
I'm going to repel.
They're going to repel from each other. So 2 things that are alike are going to repel from each other. And 2 things that are opposite of each other are going to attract. Kind of like our relationships, right? So when you were in high school, your mom said, don't date that boy or don't date that girl. She's so bad that everybody in her family's bad. Don't date them. I don't want you to date them. What did you do?
Date them.
You went and dated them, right? Regardless, you're like, but mama, I love them. That's my boo. I love them. And you had to date them. And as your mom said, they were bad, right? But you love them to death, right? So those opposites are going to attract. Your positive and your negative, they're going to come together, okay? And so this is just basically showing you that with a cloth and a glass rod. We've talked about chemical reactions already. We've already talked about the reactant. We've talked about the products. So we've also talked about coefficients. Coefficients means this is how many water molecules we have, okay? Here, this is how many hydrogen gas molecules we have. This here is understood to be 1, okay? And the plus symbol is kind of like, okay, so from water, it breaks down to hydrogen gas and oxygen, okay? So that plus is like our and. And then up here, so we have carbon plus oxygen gas yields carbon dioxide. Okay.
I have a question.
Yep.
What's the difference between O2 and 2O? Do you know what I'm talking about?
2O, like this.
And then O2.
You will never see this, right, as a chemical equation, because oxygen always has its own, it's always diatomic. So you're always going to write it like that. Do you understand?
I thought you wrote that before, so that's why I was confused.
Check. It should be O2.
Okay.
Okay. Questions? Any other questions? Okay, so let's talk about energy, right? So energy has to be conserved just like matter. So energy is basically the ability to do work or to transfer heat. Okay, so if you're burning something and you stand next to it, let's say a fire, right? Log on a fire, you stand next to it, what do you feel?
Heat.
Heat. So in that case, heat is being released from that chemical reaction, that burning reaction. That's how we get warm, right? So heat is being released. So that means that it is an exothermic reaction because heat is being released. So that means it's going to be on the product side of the equation. So this is an example of butane burning. Butane is a gas that we commonly use for it's a natural gas that we use to burn, right? So 2 molecules of butane plus 13 molecules of oxygen gas yields 8 molecules of carbon dioxide, 10 molecules of water, and energy, right? So that means that since energy is on the on the product side of the equation, since it's on the product side of the equation, it's being released. So we call that exothermic reaction because energy being released outside, okay? An endothermic reaction means that you're taking energy from the surroundings or you're absorbing energy to make the reaction happen, okay? So typically, how many of you guys run into walls or fall down or break an ankle or something like that where they have to give you a cold pack?
Yeah.
Never happened to you? Where they break it open and you put it on your leg and it's nice and cold, right?
Yes.
Cold pack is an example of an endothermic reaction. So what it does, it's absorbing all of the heat from the surroundings. And so that's the reason why it gets cold, because it's absorbing heat. So if you're absorbing heat or you're putting heat into the reaction, that's considered endothermic. An endothermic reaction is removing heat from the surrounding or absorbing heat, okay? So that means you're going to put it into the reactant. It's going to be one of the reactants, okay? Okay, so kinetic energy is the energy associated with movement, okay? So let's say I get really upset at you and I toss my coffee mug at you. Is it going to hurt? Just tossing it. I'm just like, is it really going to hurt?
No.
Now, let's say I get really mad at you and I'm like yelling and cussing and I just throw it at you, right? Really, really hard. Is it going to hurt?
Yes.
Yes. Why is it going to hurt more if I throw it harder at you than I throw it slower at you, rather than I just toss it at you?
Because there's more force behind it?
There's more force behind it, okay? Well, we know that force is a function of speed, right? So energy, according to Einstein, is equal to mc squared, where c represents the speed of light but we can break it down to something simpler to that we can understand. We can say energy is equal to mass times the velocity. It's actually 1/2. Okay, so energy equals mass times velocity. So if I'm just tossing at you, am I going really fast? Am I throwing it fast if I just toss it at you? No. So that isn't going to hurt so much. It's not going to have a lot of energy behind it. Where if I really toss it and throw it really hard, you know, I really reach back and it's going really fast. In that case, is that going to be hurt? It's going to hurt, right? In that case, so because the velocity has increased, and hence the force is going to increase, which means that the energy behind it is going to increase. Okay, you guys are good? Okay, so we can convert energy, right? So energy can be kinetic energy, it could be chemical energy, it could also be heat. Okay. And that's going to be important for law of conservation. If I get there. Oh, potential energy is, so by me holding the cup up off the ground, it has potential energy associated with the height. So since gravity is pushing down on it, and it has a mass, the higher I hold it, the more kinetic energy it can have, right? So that just represents, it has this potential energy associated with the arrangement. In the case of molecules, it would be the arrangement of particles in a system, but in the case of my mug here, it's just the arrangement where it's located at. If I drop it, it's going to become kinetic energy. That potential becomes kinetic energy. Okay, so we're changing that potential energy to kinetic energy when I drop it. I don't want to drop my coffee cup because I don't want to waste my coffee. You understand what I'm saying?
So are there other, is it only associated with gravity?
It's not only associated with gravity, but gravitational force is one of the major things that we do. But typically potential energy can be associated with just arrangement itself, its order. So we've already talked about E equals mc squared. So the law of conservation of mass and energy basically says that, you know, in terms of mass, in a chemical reaction, what you put in, you got to get out at the end, okay? And then the law of conservation of energy basically says exactly the same thing. The only thing it says that's slightly different, or that we can interpret it as being different, which it means the same thing. Ultimately, the energy that you put in the system has to be conserved. It can neither be created or nor can it be destroyed, okay? So that basically means that the only thing that you can do is you can change the form of it. So if you're using chemical energy, meaning you're breaking bonds and you're making bonds, right? That can be changed to heat. And then that can be changed to other forms. It can be changed to kinetic energy. It can be changed to electrical energy, you know, just by sitting there and doing that. Let me give you an example. So we have the chemical energy associated with natural gas. We burn natural gas, that's a chemical reaction, and heat is being released. Heat causes the water to boil. Water boiling, right, causes steam producing. Steam goes through this channel, it turns the turbine. The turbine turns the generator. The generator generates electrical energy. The electrical energy then lights up your TV, your range, and your lights, right? And so we went from chemical energy, it was converted into heat. That heat was then used to convert this steam into potential energy because those molecules are moving faster because you're generating that steam. Then that moved the turbine, kinetic energy, right? Not potential energy, kinetic energy. The kinetic energy moves the turbine, right? The turbine turning causes the generation, which again, kinetic energy, causes the generation of electrical energy. electrical energy, then powers all the stuff in our houses. Okay? So energy is never created or destroyed, it's just changed in form. Okay? Simple? Well, welcome to chemistry. So that's it.